Thank you. Yeah, I can hear you. Are you able to hear me? Thank you. Just want to make sure if my screen is shared properly. Thank you. Okay. Good morning and good afternoon, everyone. My name is Harish Chanandan, and I'm joining here from New York. I'm currently working as a software development manager at Fairportal. It's an honor to be here at Icncda 2026 at University of Essex, and I want to thank the organizer for inviting me for this keynote. Um, Today in my talk, I want to talk about something I believe is the defining challenge of our era in AI. Which is basically how do you build a system that are not just intelligent but genuinely resilient and dependable. Uh, the title of my talk is Building Resilient and Dependable AI System for Adaptive Cybersecurity to Prevent Privacy Preservation and Distributed Intelligence. Um, um, you know, Let me start with a very simple observation. We have made remarkable progress in AI over the past decade, but as the capability grows, so do the risks. The question is not, no longer whether AI can achieve remarkable performance. We all know that the question is basically that we need to ask is, can we depend on it? And when it matters the most, can we actually depend on it to solve our problems? Um, what exactly is the dependability problem? Um, as one of my peer once said, um, while many AI solutions perform well in controlled environment, they often fail under real world conditions. Actually, what that means, is, um, most of the AI systems, data is often late, incomplete, duplicate, or sometimes out of order, and where system must operate under strict latency and availability constraints. The difficult part has never been about models themselves. It's about building trust in underlying data assets. The challenges aren't abstract. Everyday industry around the world face, adaptive cyber attacks. Healthcare providers struggle to train AI on patient data without violating privacy. Logistics companies need autonomous systems that can handle real world complexity. And retailers want to personalize experience without, centralizing sensitive customer data. Here's what I've learned from my experience for the past, 2 decades. Building system that power digital experience at scale is not an easy job. And today's talk is, about that particular problem. Now, let me get into my main topic of my today's talk. Um, to build a truly dependable AI system, my research and through my experience, last 2 decades, I propose, a solution where we have three fundamental pillars. The first pillar is adaptive security. Traditional approach to cybersecurity, rely on static rules and signature. Attackers evolve faster than we can update, the defense. We need systems that learn and adapt in real time. System that treats security as continuous learning problem and not just as checklist of things. Um, the second pillar, which is privacy preservation, as AI moves to the edge to devices, hospitals, factories, we face an impossible choice: centralize data for better AI, or keep it local to protect privacy. We can and do both. The third pillar is scalable autonomy. Complex real world systems, autonomous vehicles, warehouse, robotics, distributed infrastructure requires architecture that can handle open ended environment where objectives constantly change, and often we are not able to scale and define the complexities of the system. And along with that, we'll have to add another fourth dimension to it, which is economic sustainability. Dependability means nothing if the system burns through budget uncontrollably. Coming to my first pillar, which is adaptive cybersecurity. Traditional security is like chasing a ghost with a rule book. By the time you have written the rule, the ghost has already left the building and gone for lunch. That's the real scenario we often face at big organizations. Um, and you identify as like basically you identify a threat signature, you write a rule, you deploy it. By the time you're done all that, the attacker has moved on. What if we could flip that model? My multi-paradigm framework integrates three complementary approaches. The first one is supervised learning model. Uh, the supervised learning model will be the foundation to detect that threat patterns quickly. The second one, deep learning using convolutional neural network for anomaly detection. CNN approach achieves very high accuracy with very low positive rates. And my research has confirmed statistical significance with pair t-testing. And the third one, reinforced learning for adaptive self-evolving defenses. The system learns from each interaction, becoming more resilient over time. This framework can be deployed today across industry to detect novel fraud patterns that traditional rules miss, and to identify ransom anomalies before they encrypt patients' data and so on. I mean, just to give a brief about this, why SVM, basically think of a SVM as our precision scalpel. While other models are busy learning with what a threat looks like, SVM acts as an expert classifier for known signature. It works like it's work by finding the optimal hyperplane, basically the clearest possible line in the scan. And why do we need CNN for anomaly detection? If SVM is the bouncer checking the ID, the CNN is our CCTV system with advanced analytics. That's how I would see that. In the uh, 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 pillar one, I want to go a little bit in depth about a deep Q network. Um, think of deep Q network as giving the system a survival instincts. It's learning, adapting, and most importantly, getting tired of being hacked. We can use deep Q network to dynamically allocate cybersecurity resources instead of static defense. We now have a system that treats security as Markov decision process, basically continuously learning from each breach attempt. The implication is profound. Instead of chasing the attacks, the system becomes progressively harder to breach over time. In financial institutions, the EQN-based system detects novel fraud patterns. In healthcare, the multi-paradigm approach identifies ransom anomalies before they encrypt patient data. And in e-commerce, adaptive defense stop credential stuffing attacks that change patterns daily. Getting into the pillar two, uh, we always want the benefit of central brain, but we are learning that nobody wants to give up the data to build it. Federated learning is the compromise where everyone keeps their secret, but the model still gets smarter. So, moving into the third pillar, which is the second pillar, which is the privacy preservation. Here's a challenge I see organizations struggle with daily. They want to leverage AI at edge on devices in hospitals across distributed environment, but centralizing sensitive user data for model training raises massive privacy and compliance concern. You know, generally like GDPR or HIPAA, which becomes a problem here. So we face an impossible choice: centralized data for better AI, risking privacy, or keeping data local, sacrificing intelligence. My work on federated learning, way out, federated learning allows models to learn from decentralized data without ever moving or exposing sensitive information. But here's the nuances. Edge environment have constraints, limited compute, limited bandwidth, limited battery, and they are vulnerable to attack like data poisoning and model inversion. Um, Privacy preservation, it's like having a group of experts solving a problem, but they are all in separate rooms, talking only through notes, slipped under the doors. Privacy maintains puzzle solved. That's how I quoted. Um, my research evaluated optimization strategies specifically for these resource constrained environments while addressing security vulnerability head on. Robust privacy and security to mitigate risks such as membership inference and gradients inversion. I integrated privacy preservation techniques like differential privacy and homomorphic encryption, which obfuscate model updates while ensuring data confidentiality. System integrity, we maintain model integrity against malicious updates by deploying Byzantine resilience aggregation algorithm, which identifies and filters out anomalies client input in real time. Operational efficiency, to overcome resource constraint, we apply gradient compression and energy-aware scheduling. Let's look at look at it with a real example. In healthcare, federated learning allows hospital to collaboratively train diagnostics AI on patient data without ever sharing protected healthcare information. This is a breakthrough for rare diseases detection where no single hospital has enough cases. In retail, we are seeing personalized recommendation built from on-device data without uploading customer purchase history to centralized servers. In manufacturing, factories optimize operations using federated learning while keeping proprietary production data within their own walls. With federated learning, the organization no longer have to choose between privacy and performance. Coming to the third pillar, if you have ever managed a team of developers, which most of us must have, you already understand hierarchical reinforcement learning. You give high-level goals, let the mid-level coordinate, and pray the low-level, execute actually what happens. The third pillar is scalable autonomy. Reinforcement learning has shown tremendous promise, but traditional RL breaks down when environment becomes complex and dynamic. If you're managing a warehouse robotic system, coordinating multiple autonomous vehicles, or orchestrating distributed infrastructure, you cannot have a single policy governing everything. My research introduced a three-level hierarchical reinforcement learning framework using soft actor critique. High-level goal setting and task decomposition will be done by the level one. The level two will be, the mid-level policy selection and coordination across agents. Level three or low-level actions execution with real-time adaptation. The results have given very high task success rate and cumulative rewards. This has significantly outperformed both flat RL and two-level HRL approaches. The soft actor critic architecture has delivered the highest action entropy and lowest variance, ensuring stability and adaptive control even in complex open-ended environment. Uh, I want to talk a little bit more about HRL approach and the economic impact of uh, setting up infrastructure with with the three pillars that I've explained so far. As you know, there are companies who burn millions in a month on uncontrolled agentic calls. That's not a business strategy. It's like a delete my budget button. Use RAG or what you want to use. You can use MCP server, but you always need to keep an eye on the invoice. Uh, so I want to shift our focus from capability to economics. Uh, in my research or the framework that I've developed, um, HRL basically uses uh, two important paradigms that we use very common in AI world these days, which is RAG and MCP. Uh, let's be clear, they both actually solve different problems. RAG is like fundamentally about connecting an LLM to knowledge, your company's policies, product documentation, internal wiki. It's a semantic search and search and generate pattern. MCP, on the other hand, is a protocol for action. It's like it allows an AI agent to call API, query live database, and trigger workflows. It turns the model from a thinker into a doer. The industry narrative is increasingly pushing MCP for everything. But here is the critical insight from my experience. MCP does not replace RAG, and the blind rush to adopt full MCP or agentic framework for all the tasks is a recipe for budget crisis. Um, so, looking at the data, a direct comparison of MCP keyword search versus a RAG semantic search on the same document shows that MCP use more or triple the token and cost per query and network calls and bandwidth utilization. So we have to be very mindful while using these technologies in the real world, simply because it dumps the entire unprocessed document into the context window. Second, the schema overhead. MCP introduced very high cost with the schema overhead. And also third, and the most critical one is the viral loop. Agentic MCP flows are inherently iterative. They can fall into loops where one tool calls another, or they repeatedly fetch some data. These loops are invisible to standard infrastructure monitoring, but they show up dramatically on the invoice. Okay, to conclude what I was, presenting today, um, my framework, it's like building a high performance car. You need the engine, which is the HR, the fuel, which is the RAG, and the steering wheel, which is the MCP. But you also need the seat belt, which is the cybersecurity, and the fuel gauge, which is the economics. Now, let's bring together everything into an unified framework. This architecture integrates HRL, RAG, MCP into a single coherent system. HRL, which is a three-level framework, serves as a central coordinator, the brain that makes decision, delegates tasks, and orchestrates agent. RAG provides the knowledge, which is retrieving relevant information to ground decision in facts and evidence. MCP provides the hands executing tools and taking real world action. Cybersecurity protects every layer from data retrieval to tool execution. Privacy preservation with federated learning ensures sensitive data never leaves its source. Economic sustainability ensures the systems stay within budget, with HRL coordinator deciding when to retrieve and when to act. Okay, let me go into let me show you how this work in a single powerful use case, the smart hospital of the future. We have an adaptive cybersecurity, the immune system, harden the hospital network against ransomware by proactively monitoring IoT medical devices and data pipeline. Privacy preserving intelligence, the collective brain. Federated learning allows multiple hospitals to train a global intrusion detection system on shared threat patterns without exposing local hospital network logs or PHI. HR, three-level coordinator, and orchestrate the hospital's infrastructure agents. The goal, the level one, which is the goal, defines security posture or uptime requirements. Level two, the coordination, coordinate network security patching and resource allocation agents. Level three, which is action, execute specific defense protocols. The RAG, the security intel, retrieves real-time threat intel, CV database, and internal network security policy to ground defensive decision in verified facts. The MCP, which will act as a security response, triggers immediate proactive actions like segmenting a compromised network, updating firewall rules, or isolating infected IoT medical devices. And overall, the economic sustainability, the HR coordinator balances the cost of security action, example, bandwidth for patching versus risk of downtime, managing budget and operational loading when to utilize RAG, the knowledge retrieval, versus when to trigger MCP costly tool execution to maintain budget efficiently. And for me, this is the future of dependable AI, secure, private, autonomous, and sustainable. And with that, my today's keynotes, ends over here. I hope everyone had a pleasant, presentation listening to me, and hope other keynote speakers also have a very good, evening today, presenting uh, their speak. Thank you so much.
Sir Roshan Jahan here. Am I audible, sir? Sir Roshan Jahan here, sir. Okay, now let's proceed to Sir Sai Saket Cherikuri. Sir Sai Saket.
Hello, can you hear me?
Yes, sir. Sir, now the floor is yours. Please proceed with your presentation.
Thank you. Is my screen visible to everyone?
Yes, sir, it is visible. You may proceed.
Thank you. Good morning, everyone. And I just want to take this opportunity to thank the organizers for giving me this opportunity to talk in the Icncda 2026. Um, Today, I'll be talking about my paper, which is KV Scope, Visualizing KV Cache Dynamics in LLM Inference. I'm a AI engineer, and my designation is a ML systems and LLM researcher, and I'm an independent researcher. Um, I'm joining in from Washington, D.C. in the United States. So before we get to the talk, I just want to give a brief idea about what what this talk is about. So nowadays, as the last esteemed speaker has pointed out, AI has developed at a rapid pace. Even over the past 2 or 3 days as well, we've had a lot of we have had a lot of improvement in the AI sphere. So um, something that isn't very public facing is that a lot of these companies, they tell you that oh, we have the best model and it's the smartest model. It can solve this, it can solve that, but at what cost? What how do you run all of these large servers and all these large models on hardware? And this talk is going to give like a useful insight into how this all of this works. So my talk is going to be scheduled about the challenges as of LLM inference, KV cache behavior, existing profiling architectures. What software already exists so that we can use that software to profile what is already going on the hardware. Um, Profiling software usually helps. For example, if you have some model running on a hardware, um, it doesn't tell you what is going on exactly. So you use different profiling softwares to see what goes on under the hood and then get a better idea of what's going on. Then we have experimental evaluation, the results of the experiment, the case studies, and future roadmap. So just to give an idea again of what this paper is, large language models have become, very fundamental to AI applications at the modern stage. But serving these models is what becomes a significant challenge, and it is a main pain point for many of the companies these days. Nowadays, a lot of the companies are shifting from uh, shipping the most capable model to the most efficient model. Um, Token usage has become a huge um, pain point for a lot of these companies. Over the past few years or the past few months, companies have been given enterprise access to a lot of these large language models, and as a result of that, as a result of the pay-as-you-go pricing scheme, a lot of the employees have been using and burning tokens at an astonishing rate. As a result, rate limits have become a huge problem for a lot of these companies, and a lot of um, enterprises and corporations are paying a lot of money, which they do not need to pay because of simply the way the model is not efficient enough. And another reason for that is because a lot of these models, the way they're served and the way they're running on the hardware is not as efficient as it could be yet. So what we want to do here is introduce a new open source and profiling visualization framework called KV Scope. So what this does, it correlates KV cache allocation, scheduler queue dynamics, GPU telemetry of whatever um, traces the GPU gives us, um, and inference telemetry such as and performance metrics like time to first token, time per output token, um, when you which basically tell us that the moment you send a prompt, how much time does it take for the LLM to give a response? That is a time to first token. And time per output token is the time between each token. Like if you have a sentence, how much time does each word in the sentence take? So what we want to do with this tool, KV Scope, is to give the developers an idea of, okay, you have a model running on, say, your um, server, but then what are these metrics that the model tells us? How do you optimize what you are already running? Instead of buying more hardware, how do you use the most of the hardware that is already existing? So we use this tool to enable faster debugging, analysis, and latency optimization. And the target user is any developer, and the use case is for production scale LLM deployments. So, like I was saying earlier, the inference demands a lot of uh, high computation, and that's not something that is readily available these days. The prices of hardware has skyrocketed as well, and as a result, making use the most use of the available hardware is important. And another thing to consider as well is increasing prompts significantly increases KV cache requirements. So just as a refresher, KV cache is essentially um, the way that these models work is that whenever you give a model a prompt and you want to get the output, what it does is it uses attention, the attention mechanism, and it looks at all the previous prompts, all the previous tokens before that. So normally what you would need to do is when you want to generate one token, you look at all the previous tokens, and then when you want to do the next one, you look at everything else, and then you recompute the key and value pairs. But that's very computationally expensive, and it's not realistic for most of the use cases, and it's very computationally and it's very computationally expensive, as well as it has a big hit on your storage because you have to keep looking at each token and to save those uh, values. So KV cache essentially is just the cache for these key and value uh, values. So you keep them in the cache instead of instead of doing recomputation for all the tokens over and over again for each prompt and for each generation of the next token. So that is the basic uh, use case of KV cache. So when we increase the prompt length, what that does is essentially um, you have to store more data from that prompt in the cache. So you might have seen a lot of these large language models that have context sizes. For example, some of the smaller models might have something like um, 32,000 tokens, but nowadays the frontier models have almost 128,000 or even 1 million token context length. So what this basically is that it tells you how much of the KV cache you can store, how many tokens you can store in one single prompt. So high concurrency creates scheduler bottlenecks and GPU memory pressure. The more users you have for your model that are actively queuing the model, querying the model, getting responses. So that's where the scheduler bottlenecks, and then it has a hard time um, scheduling the traffic that comes in and distributing across different servers and getting the response back. So this creates GPU memory pressure. Existing monitoring tools fail to correlate hardware metrics with inference behavior. So you might see a classic example of this is that you might be your customers are complaining that I'm typing my prompt and it takes like 20 seconds to get back the response. So as for a real time chatbot, this is a huge problem. You cannot have customers waiting more than 20 seconds to get back the first response. Um, because that would make them frustrated and not want to use your application. So you want to debug what's going on. So you go and check the server, and you see that okay, my GPU is being utilized 100%. So what is going on? But the reality is that these GPU metrics do not paint the entire picture, because there may be various other factors, such as the prefill phase and the decode phase getting bottlenecked. As a result, these might not these metrics are not exposed by the LLM. As a result, you do not know what is going on exactly. So hardware metrics do not correlate with inference behavior. So the main use of this tool is to have a universal observability that is essential for diagnosing and optimizing LLM serving systems. So just as a literature review, these were the main papers that I had looked into to build this tool. Of course, the first one that most of us will be familiar with is "Attention is All You Need" by Waswani et al. And the main contribution of this paper is transformer architecture and self-attention, which is the main underlying hardware and underlying architecture behind all of modern LLM systems. And next one is NVIDIA's official documentation. So it provided me assistance with GPU profiling and telemetry. Like, how do you read the data that you get from the profiler? NVIDIA offers NVIDIA Nsight systems and Nsight Compute, which are two different profilers which you can use to debug your, which you can use to profile your models on any NVIDIA hardware. Then I referenced two other two other projects. Sorry, VLLM project and TensorRT LLM. So VLLM project is an open source, high performance LLM serving platform, efficient LLM serving platform. So what the main this is VLLM is the main um, serving engine behind KV Scope. So page attention is what is its most important feature. So we were discussing about how KV cache is used to store the different key and value pairs. So what VLLM does is it it uses the paging concept from operating systems, with which many of us must be familiar with. The virtualization of the KV cache allows us to have use much more memory than is physically available. So some current gaps in this research in this research is that there is limited visibility into KV cache allocation dynamics. We do not know exactly how and where the KV blocks sit in the memory. So that is something that is missing in the current research landscape. Then there's a lack of correlation between GPU telemetry and inference latency. Like I had explained earlier, um, GPU uh, telemetry tells you one thing, but that's not the entire picture, because there are a lot of other factors, like the time to first token, time per output token, and different latencies that are part of the entire inference stack that are not um, that the GPU does not tell you exactly, and there's no way to correlate one and the other to get a different to draw a conclusion. So that is what we aim to do. um, Existing profilers operate independently at hardware or application levels. So you have uh, PyTorch profiling, you have PyTorch debugging, then you have VLLM, which gives you its own metrics. At the same time, you have Nsight compute and Nsight systems, which NVIDIA gives you, so that you can uh, profile your GPUs. But the difference is that these are all at different levels. So the NVIDIA profilers are at a more hardware level, and the VLLM metrics are at like an application level. So the gap is to the main problem here is to bridge the gap between both of these two, and then get a useful conclusion between the two of them, and like draw some insights. Scheduler queue behavior remains difficult to diagnose. as concurrency increases and as the number of users increases, it becomes more and more difficult to for the scheduler to distribute the tasks across different models, and while at the same time hitting the required latency and service level objectives. Few tools provide real-time full stack profiling for production LLM serving. So as the market stands right now, there are not many open source tools that provide a developer a way to get insight into the entire LLM serving stack. You might have specific tools such as like I mentioned earlier, NVIDIA's Insight and VLLM's metrics and SGLang's metrics and Grafana, Prometheus metrics, etc. But a few of them if only a few of them provide you with the entire stack, so you can have one dashboard with everything that you need. So what I propose in this KV scope project is that suppose you have your LLM, it's running on a server. Um, you first you get the metrics from the server. Suppose we have a serving engine of VLLM or TensorRT LLM. You optimize the model execution and batch management. That's what you do before deploying the server. And then you have lightweight event hooks that hook onto the server, and they collect non-blocking telemetry collectors such as request lifecycles, KV cache allocation, and scheduler events. So what this basically means is that you have your model running on a server. Um, then we decide what serving engine it is. Suppose we say it's VLLM. Then we have um, hooks that hook onto the model, like they attach to the running model already, and you collect telemetry data from that. For example, you collect um, what requests were sent to the model, where the KV cache is allocated, the different scheduler events that take place, and those sort of things, the output sequence length, the input sequence length, and those sort of things. And then the next stage is the time series aggregation engine. So this is important because what it does is it synchronizes raw metric streams across microsecond timelines. What that means is that you have your data from the lightweight event hooks, but then that doesn't mean anything until it has a timestamp to it. Suppose you say that, okay, I'm getting a lot of requests, um, but then when you look at this at the end of the profiling session, you see that, okay, I had 100 requests. I had 101 requests. But then unless you pair it with timestamp data, that's when it tells you, okay, I had 100 requests at the first second, and I had only one request for the next 20 seconds. So that tells you that something is wrong. Without the time data, you wouldn't know. You just know that you had 101 requests over, like, say, 20 seconds. But you don't know when and how many requests happen at what time. So that's what's important. Then after that, we correlate all of this data into an interactive KV-scope dashboard. So what this tool does, KV-scope, is it's an interactive dashboard that tells you data in real time. It tells you the KV cache pressure, how much of the cache is being used, and based on the hook data and the time series aggregation, it provides its response. It provides its analysis in real time. Suppose we have um, a high latency for time first token, then it would tell you, okay, maybe there's a long prompt. There's the it's getting stalled in the pre-flow stage, which probably means that there is a large prompt incoming, and you might need to split the prompt into smaller bits and chunks to improve the time to first token latency. And similarly, you have different metrics like time per output token and GPU, VRAM utilization, GPU utilization, as well as queue length. So these metrics are what you could see on the dashboard. And finally, once the entire run is over, it collects all of the data, and based on a few parameters, you can decide and you can analyze the data, and you can come to a conclusion you can see what actually happened and at what time. So then you can isolate different incidents such as thrashing, scheduler bottlenecks, and optimize your latency and get the best serving from the hardware that you have available. So based on our discussion, based on our experiments, we could find we could zero down on a few issues. So I think the most obvious one is a long long GPU memory pressure, um, which basically means that the GPU is being utilized a lot. So that was usually due to bad KV cache allocation, and the expected improvement is better VRAM utilization after using KV scope. So a developer could see that I'm having high GPU pressure, and using KV scope, they could see that the reason would be bad KV allocation, and not any other reason. So the best way to tackle this is change the configuration of of the LLM, and therefore you have better VRAM utilization. We have a few other metrics as well, such as long TTFD, uh, and KV Scoop would analyze that this is due to scheduler queue bottlenecks. And if you, as a developer, target the schedule queue, then you would expect an improvement of faster time to first token. Um, Next, we have the high time per output token. So um, if this was the issue of the server and a developer used KV Scope to analyze the server, what he would want to do is target the KV cache and see where it's being allocated and see different ways to optimize that. And then if you would do that, you could expect an improved token generation. Um, so the basic thing in this is a lot of these things boil down to the KV cache being not being allocated as efficiently as possible. But that's just a blanket statement, and it's not as easy to diagnose what is going on under the hood. So KV scope tells you that if I have an issue, say tail latency, it tells me what do I need to look at, what do I need to optimize to get the best performance. So that is the main uh, use case for this tool. So just to compare what is all the other traditional profiling tools with what KV Scope offers. Traditional profiling offers only hardware metrics, separate monitoring tools, average latency analysis. It doesn't give you different prefill and decode stage um, latency analysis. It's static. KV Scope is in real time, and it's limited root cause in the sense that it doesn't correlate, like I said earlier, it doesn't correlate the um, data between the GPU telemetry as well as inference latency, and that's what KV Scope aims to do. It tells you the issue and it tells you what to target, and it's not independent. It's independent because there are different levels of hardware abstraction. Since KV Scope aims to unify all of that, we are able to get a synchronized timeline visualization. So just to conclude my talk, KV Scope is a project that aims to um, target developers who are into LLM inference serving, and KV cache behavior is the primary factor affecting LLM inference performance. So optimizing that is always the first choice and the best choice. It Existing frameworks do not existing profiling tools do not allow you to correlate GPU performance, GPU telemetry, as well as inference performance, and that's what model KV Scope does. It provides separate TTFT and TPOT latency data, which provides more accurate performance diagnosis, cross-layer telemetry, significantly improving bottleneck identification, and it enables a unified observability across different serving engines and GPU hardware. So you get an idea um, using different hardware. You can use the same tool across different hardware and different models, it's model and hardware agnostic, which means that you can use the same tool for any model and any hardware, and you would still get the same results. So future work includes expanding this into different serving frameworks like SGLang and LM deploy and a TensorRT LLM, and of course multi GPU distributed profiling. A lot of these models these days are not run on a single GPU. They run on a fleet of GPUs, almost an entire server rack. So what would be useful is to test this on multi GPU distributed systems, and then maybe an AI driven anomaly detection. If the budget allows, use the LLM that it's hooked onto to analyze the results in real time and give you performance data. So that is definitely something that would improve this a lot. Um, then static detection, like predictive scheduler optimization, something like how you have branch prediction in uh, computer architecture. So predictive scheduler optimization would do some preemptive optimizations before we reach that stage. And the support for disaggregated pre-fill decode architectures is something that needs to be looked into as well, because running pre-fill and decode disaggregated has shown a lot of improvement as per data that is readily that is available at this day and time. So that is something that definitely needs to be looked into. And of course, last but not least, community-driven open source development is a must for tools like this, that since it provides transparency and lets the user build what they want for their specific use case as well. So that's it for today. I just wanted to take this opportunity for to thank the organizers for letting me speak in this conference, the Icncda 2026, and I hope everyone had a nice listening session. Thank you. Bye bye.
Thank you, sir, for delivering such an insightful and inspiring talk. We sincerely appreciate your time, valuable expertise, and the knowledge you have shared with us today. Thank you, sir. With that, I would like to invite our next distinguished speaker, Ma'am Roshan Jahan Bhuiyan. Ma'am, am I audible? Ma'am Roshan Jahan Bhuiyan?
Hello, can you hear me?
Yes, ma'am.
Yeah. I
The
have
floor is
some
yours.
issue in my network.
Oh,
So
okay,
can I
ma'am.
speak later? I am facing some
Uh,
issue, technical issue.
Okay, ma'am. Okay, ma'am. Okay, ma'am. Okay, ma'am. Sir, Sushant Kumar Sahu. Sir, Sushant, sir. Welcome, sir. So the floor is yours now. Please proceed with your presentation. So you are not audible at the moment. Sir, you are not audible, sir. We would like to invite our next distinguished speaker, Sir Ranjan Mahanti. Sir Ranjan, sir, am I audible?
Yes, am I audible now?
Yes, sir. Good afternoon, sir. So the floor is yours. Please proceed with your presentation, sir.
Thank you so much. Just give me a second to share my screen. So my screen is visible to everyone. Morning, everyone. It is my pleasure to welcome you all to this session. My name is Ranjan Mohanty, and I serve as an engineering manager as well as a enterprise architect at CTS Tech. I have more than 22 years of experience in enterprise application architecture, cloud platforms, API modernization, cybersecurity, DevOps, data platforms, API modernizations, and cybersecurities. So basically, throughout my career, I have worked with organizations that require highly secure, scalable, and resilient enterprise systems, particularly within the healthcare domain and financial domains. Today, I will share my perspective on how distributed cloud computing is evolving beyond traditional multi-cloud environments into AI native architectures that drive enterprise digital transformation. Uh, so now I will explain how artificial intelligence is reshaping distributed cloud systems by introducing intelligent automation, predictive analytics, and autonomous operations. Uh, as organizations increasingly adopting hybrid and multi-cloud environments, they also face challenges related to governance, interoperability, scalability, and security. Drawing upon my experience at CTS Tech and all previous CMM5 level companies where I worked, I will explain how cloud native technologies, Kubernetes, API fast integration, DevOps, and AI work together to build resilient. Sorry, work together to build resilient enterprise platforms. I'll also demonstrate how these technologies improve API interoperability, optimize infrastructure utilization, and strengthen cybersecurity. So, giving an introduction to this particular topic that I'm going to discuss about, it's related to enterprise computing is undergoing major transformation. Organizations are moving away from monolithic applications towards cloud native and distributed architectures that provide greater scalability, resilience, and business agility. In my role, I regularly work with enterprise platforms that integrate critical systems, data platforms, and AI services across hybrid cloud environments. This practical experience reinforces the importance of designing architectures that are secure and intelligent. I believe artificial intelligence is no longer simply another technology component. It has become an essential architectural capability that enables predictive monitoring, automated operations, and better decision making. Coming to literature review, I I have let me discuss the existing body of research that forms the foundation of this work. Cost contribution of Unbrushed and his colleagues established the principles of cloud computing, while Bonds and his team demonstrate how Kubernetes transforms container orchestrations. Research from Google, Microsoft, IBM, and the Cloud Native Computing Foundation highlights distributed cloud computing, zero trust security, AI ops, and cloud native engineering. I relate this concept to enterprise architecture projects that I have led, where similar technologies improve scalability, governance, and efficiency. So let's discuss about the research gaps currently regarding this artificial intelligence presence of software development SDLC life cycles. So although significant progress has been made, important research gaps will still exist. Uh, Many studies examine artificial intelligence and cloud computing separately rather than considering them as integrated enterprise ecosystems. Organizations continue to struggle with multi-cloud governance, security, intelligent workload management, and sustainability. From my professional experience, I observed that many cloud migration programs succeed technically but fail to establish intelligent operational frameworks. This gap motivates the proposed architecture presented today. And this topic also already have been discussed by previous our two esteemed authors. So we are all talking about the same discussions that AI is still needs some improvement. My proposed methodology is the architecture begins with enterprise applications communicating securely through a API gateway before interacting with cloud native microservices deployed in Kubernetes clusters. Artificial intelligence continuously analyzes telemetry, application performance, and operational metrics to optimize workloads. Distributed data platforms support hybrid and multi-cloud environments, while AI ops automates monitoring, incident detection, and remediation. This methodology reflects architectural principles that I apply when designing secure, scalable enterprise solutions for complex healthcare and financial environments. So by applying these architectures, the results and discussions are like this. The proposed framework demonstrates several enterprise benefits. AI-driven optimization reduces infrastructure cost by improving resource utilization. Predictive monitoring increases system availability by identifying issues before they affect users. Intelligent automation accelerates incident response and reduces manual operations effort. Zero trust architecture combined with AI-driven threat detection strengthens cybersecurity, while API-first integration improves interoperability across enterprise applications. These outcomes align closely with the environment that organizations seek during digital transformation initiatives. So this slide presents the comparative analysis with the monolithic and old architecture with the current proposed AI native architecture. So when I compare traditional cloud environments with AI native distributed cloud architectures, the differences are clear. Traditional platforms really have rely heavily on manual administration and reactive monitoring. AI native environments continuously optimize workloads, automate deployments, and predict operational risks. I believe enterprise architects must now design intelligent ecosystems rather than simply deploying infrastructure. This shift enables organizations to become more agile, resilient, and innovative. Concluding my work, AI native distributed cloud architectures represent the future of enterprise computing. By integrating artificial intelligence, Kubernetes, DevOps, cloud native engineering, and API first design, organizations achieve greater scalability, resilience, security, and operational efficiency. Looking ahead, I see executing of exciting opportunities in agentic AI, explainable AI, and federated learning, uh, and cloud computing with quantum ready infrastructure. Um, I think thank you for your attention. I have completed my presentation. I appreciate the opportunity to share my research and professional expertise, and I welcome your questions and if anything. Thank you.
Thank you, sir, for delivering such an insightful and inspiring invited talk. We sincerely appreciate your time, valuable expertise, and the knowledge you have shared with us today. With that, it would be my great pleasure to invite our next distinguished speaker, Sir Susant Kumar Sahu. Sir, I hope your issue has been resolved. No, sir, you are not audible actually.
Hello, can you hear me now?
Yes, sir. So you're audible, sir.
Okay, thank you. Sorry for that. There is some technical
So
glitch
the
on my.
floor is now yours. You can proceed with your presentation.
Thank you. I hope you can see my screen, right? Yeah. Hey, good morning, good afternoon, across all the globe. Um, Thank you for inviting me to this nice presentation. So, like, it's pleasure to be here in the International Conference on Network Computing Systems and Data Analytics. Myself, Sushant Kumar Sahu. I have almost 21 years of experience into IT. Currently, I'm working as IT advisor application designer as Genwell Technologies US. So I spent most of time towards healthcare, like system enhancement, build up new tech stocks, and how we can modernize the legacy platform, delivering technology solutions for healthcare and government programs. So today I'll share practical insights from the industry on how predictive analytics, generative AI and cloud native architectures are transforming healthcare enterprises. So rather than focusing on the theoretical concepts, I will discuss how organizations can successfully integrate these technologies to improve decision making, operational efficiency, and regulatory compliance, uh, along with patient center services. So let's go to the next slide. So my agenda. So in this presentation, I'll begin by discussing the current state of digital transformation in healthcare. I will then explain the major challenges faced by enterprise healthcare systems before exploring how predictive analytics and generative AI are helping organizations make smarter decisions. After that, I will introduce a cloud-native enterprise architecture solution for large healthcare programs, followed by industry case study, and I'll have some major business benefits, future opportunities,
and I'll conclude my recommendations. Then coming to next, I have abstracts for this presentation and the demonstrations that I am going to have. So it's basically healthcare organizations are generating unprecedented volumes of structured and unstructured data from claims processing, electronic health records, and provider sorry provider related information. So for across the globe, there are multiple issues when we provide carrier and coverage related informations, and there are some human related issues are there, I mean, when entering the information through that, right? So we're just trying to see how the industry case study those parameters, and what are the major business benefits and the future opportunities are available. So to that, I can say how the traditional architecture struggle to convert this data into timely insights. A modern enterprise platform combine predictive analysis with AI-driven automation and cloud-native infrastructure to enable proactive rather than reactive decision making. You know? So these technologies allow healthcare organizations to improve operational performance while maintaining compliance, security, and scalability. So now, to give more insights to that, when healthcare systems are under continuous pressure to reduce costs, improve patient outcomes, and respond more quickly to changing regulations. At the same time, many organizations still spend on legacy applications, so that they want to continue the existing process and that are not designed for today's data intensive environment. So to improve that, we have to implement the AI-driven approach. So modernization is therefore essential. By adopting cloud-native applications, API-driven integration, predictive analytics, and AI-assisted software engineering, um, organizations can become more agile while delivering reliable digital services to citizens and healthcare providers. So these are the basic informations that I have placed here, like how the I captured number of data sets, and how I validated the outpatient, inpatients, and what is their um, like uh, estimations with respect to all the parameters that provided. So based upon the AI, I just captured these inputs here. So then coming to my next slide, it is industry landscape. So how exactly we are going to modernize the process? So across the industry, we continue to observe common challenges. Legacy applications increase maintenance cost and reduce flexibility. Data often exist in isolated silos, limiting enterprise-wide visibility. Decision-making frequently depends on manual processes that delay response and increases operational risk as well. So rising cybersecurity threats and increasingly complex regulations demand stronger governance. These challenges create an opportunity for organizations to redesign enterprise architecture around data, intelligence, and automation. So, while we are still relying on the existing legacy system, at the same time, we are trying to implement and enhance the existing process by using the AI. So, next is my research gap and opportunity. So, how it is different from the existing legacy system, and what are the opportunities and growth we can see while implementing the AI. So although AI adoption is accelerating, many organizations have not fully integrated predictive analytics into operational workflows. Explainable AI remains essential for healthcare because recommendations must be transparent and trustworthy. So we have to have enough number of test data available or test case to be prepared and get ready so that we can put it in the production system. So another significant opportunity lies in combining generative AI with enterprise software engineering to accelerate documentation, testing, code generation, and knowledge management while ensuring strong governance. Cloud native architecture basically provides the scalability needed to support these kind of innovations. So most of the AI models that we discussed, our previous guest speakers, so they gave more insights about how the AI is going to useful and what are the models they are going to use. So definitely, like that is going to helpful across uh, industry. So now coming to my next style is enterprise framework. So this framework begins by collecting information from multiple healthcare data sources, as I mentioned before. So the data is integrated into a secure cloud platform where governance and quality controls are applied. So predictive analytics model identifies patterns and quality controls are applied. Predictive, uh, it also estimate future demands, detect fraud, and support operational planning. So generative AI assists developers, business analysts, and supports team by automating documentation and accelerating software delivery. Finally, decision support dashboards provide actionable insights to administrators, program managers, and executive leadership. So this is about the framework, how exactly we can build. So now it is coming to industry case study. So drawing upon, if you see here, how exactly we can um, use the of our system to build the process. So industry case study drawings upon enterprise healthcare projects, predictive models can improve claims processing, identify fraudulent activities, forecast resource utilization, and support evidence-based planning. So AI-assisted program development shortens delivery cycles, while cloud-native deployment improves scalability and resilience. The combination of these capabilities enables healthcare organizations to respond faster to changing business needs while maintaining compliance with healthcare standards, what we have HIPAA standards, basically we say, and all the regulations. So this is the industry case study that I have. Then coming to the next, I have what is the comparative analysis. By seeing this multiple platforms and what are the cloud enterprise, we have different vectors. Like we try to find out how the decision making is going to happen, how the data integration is going to happen, then development life cycle, what should be um, by using the AI, then system scalability and security and governance, which is one of the major domain. So then coming to measurable benefits. So compared with traditional enterprise systems, intelligent healthcare platforms provide faster and more accurate decision making, improved forecasting, lower operational costs, better utilization of resources, stronger citizen engagement, and enhanced organization resilience. The greatest value is achieved when predictive analytics, enterprise architecture, and AI are implemented together as an integrated digital transformation strategy rather than implementing as an isolated initiative or systems. So these are the basic benefits. So if you see how we are moving like faster decisions making, then how much operations overhead we are reducing, then delivery, how fast we are going to do, then platform resilience. So all these are benefits that we are going to get if we go towards this AI implementation. So coming to the next, I'll have my conclusions here. So in conclusion, the future of healthcare enterprise will be driven by intelligent decision support system powered by predictive analytics, generative AI, and cloud native technologies. Organizations that successfully modernize their enterprise architecture will be better positioned to deliver efficient, secure, scalable, and patient-centered healthcare services. So looking ahead, a responsible AI, federated learning, explainable analytics, and autonomous decision support will become increasingly important area here for both industry and academic collaborations. So this is all about the discussions that I have here. Then next is closing remarks and questions. So thank you for much your attention. I hope this presentation has provided practical insights how the enterprise architecture and AI can work together to transform our existing healthcare systems. So I look forward for your questions if you have anything else. Thank you so much.
Thank you, sir, for delivering such an insightful and inspiring invited talk. We sincerely appreciate your time, valuable expertise, and the knowledge you have shared with us. With that, I would like to proceed further to our next distinguished speaker, Ma'am Roshan Jahan Bhuiya.
Yes, I'm ready.
Ma'am, now the floor is yours. Please proceed with your presentation.
Hello, good morning. I'm Roshan Jahanbhia. I am speaking from Atlantic City, New Jersey. I'm presenting my slide now. Can you see my slide? Okay. Uh, I am a doctoral researcher in artificial intelligence and machine learning. Uh, I'm currently, uh, working in University of Potomac. It's Washington D.C., USA. I'm speaking from one of my recent published paper about the early detection of cancer, especially the breast cancer, uh, by using the AI. So, why the early detection is matters? Because if breast cancer or any kind of cancer we can detect earlier, then the survival rate increase. Because after a certain period of time, uh, if we detect the cancer, then the cancer spread and the patient can take the next step sometime. So I'm talking that how can AI can help us to detect cancer earlier and increase the survival rate of a patient. Is find the critical clinical goal. It reduce the system goals such as the diagnosis cost or the time. So reducing the extra time will be uh, very effective for the patient. The screening challenge of AI. So lesion may be hidden or virtually subtle. Different radiologists may weigh finding differently. High volume, sometimes high volume of data come from the screening process and is distract the clinical staff to focus. And false positive. Sometimes unnecessary recall create anxiety and cost for the patient. False negative. Missed cancer can delay the treatment. Equity gaps, access, follow-up, and dataset representation. Right? So, what AI can learn from this process? Uh, so, mammogram, then processing, deep learning, heat map explanation, risk score, and finally clinical decision get done by the AI. So, model family, classical machine learning. I use for model SBM, random forest, logistic regression, and multimodal. So they work well on structured clinical feature and extracted image features. And deep CNNs such as RaceNet, EfficientNet, and DenseNet. They learn visual signature from mammograms, ultrasound, sound, or MRI. And multimodal AI, they analyze the image and demographics plus history of the patient. They combine the image signals with patient level risk context and explainable AI, such as GradCam, Sharp, and calibration, they makes model focus and uncertainty interpretable for clinical use. Mm, There is a research pipeline. So data curate image and clinical level. They train the model and train and develop a model with class balance, validate, test across external cohorts, explain, and finally deploy human in the loop workflow. So mm, uh, Loke held out test set, measure subgroup performance, calibrate probabilities, and validate on data from another institution before clinical claims. This is a graph. So I use four model to compare which model is best performance. So SBM was below 95%. Random forest is nearly 95%, and CNN crossed the 97%, and multimodal they had the best performance. The 97.5% was their performance. Explainability. Um, Explainability is not a decoration. It is the bridge between algorithm, evidence, and clinical accountability. So heat maps localize suspicious regions for review. Calibration show whether predicted risk matches or observed risk. Uncertainty flag cases requiring second reading. Subgroup analysis help detect bias before deployment. Here's the comparison between the radiologist and AI, and where's the gap and where AI can help us. AI can track normal exam for faster reporting. AI can prompt second review for subtle finding. AI can help personalize screening intervals. Clinicians remain responsible for final decision. So, radiologists take context, judgment, communication, AI pattern detection. They do the pattern detection and consistency. And there is a middle, a second reader prioritization, risk satisfied follow up. This will be done by the clinical staff. From model to clinical implementation, integration. mm, PEGs, RIS connections, secure data flow, downtime plan, governance, model versioning, audit trail, and clinical oversight, safety, threshold policy, escalation rules, failure monitoring, equity, representative data, subgroup metrics, accessibility, training, radiologist onboarding, and feedback loop. So implementation principle is begin with a narrow measurable use case and expand only after local evidence shows safety and value. Responsible AI. So data bias. Train and test across age, race, breast density, device vendors, and institutions. Privacy. Use de-identification, secure compute, federated learning where appropriate. Regulation, document intended use, validation evidence, updates, and post market monitoring. Accountability, define who acts, who overrides, and who reviews the error. So, future research direction is multimodal risk models combining mammography, ultrasound, MRI, family history of patient, mm, genomics, and clinical variables, and lightweight models for low resource setting using pruning, quantization, and knowledge distillation, federated learning networks so hospital can collaborate without sharing patient raw data. Prospective trial measuring patient outcomes, workflow efficiency, cost, and trust. Equity fast dataset and transparent reporting standard for subgroup performance. The future of breast cancer screening is not AI alone. It is clinically governed, explainable AI that helps experts find cancer earlier, reduce avoidable burden, and personalize the care. So, final uh, sentence is detect earlier, decide better, and treat sooner. This is the main purpose of AI in detecting the breast cancer. So this was my all of my presentation. Thank you so much. If any question, I am here.
Thank you, ma'am, for delivering such an insightful and inspiring invited talk. We sincerely appreciate your time, valuable expertise, and the knowledge you have shared with us today. Thank you to all the speakers on behalf of organizing committee.
Thank you very much.
We sincerely appreciate your time, valuable expertise, and the knowledge everyone has shared with us today. With this, we would like to conclude session S2 on behalf of the organizing committee. Thank you once again for your valuable contribution to ICNCDA 2026. Have a wonderful day ahead.
Thank you.
Thank
Thank
you.
you.
Bye.
Thank you. Bye.